So now we're going to look at these two sets of metrics. And one very important step that you should go through is compare the training performance to the validation performance. Why is that? If the performance is drastically different, usually in the direction that the training fit is excellent, but the validation fit is quite bad, it means that your model is overfitting the training data. It means that you're not able to generalize beyond your training data with this particular model. And that should be a red sign, a red signal. So comparing these two sets of summaries of performance on the training and the validation is a crucial validation step. Let me get into the important step of variable selection, also called model selection. You might have heard this earlier in the statistics course, but when you have a set of predictors and you're not sure which subset is going to prove the best one, there are methods that are algorithmic that will try all kinds of possibilities and choose a subset that is optimal in some sense. This type of variable selection is extremely useful in predictive tasks. And in particular, when we're using linear regression, there's a method called stepwise. And stepwise selection does exactly that. It goes over all your predictors and it tries different combinations in a computationally smart way so that in the end it can tell you here is the subset that gives you the best predictive accuracy. There are a bunch of different types of algorithms such as backward elimination or forward selection. If you have a small data set or an extremely strong computer, you can also try exhaustive search, which means try all the possible combinations of pairs of predictors, of triplets, and so on. The result that XOMiner will give you in this case is it will show you the top performing model with 2 predictors, with 3 predictors, with 4 predictors, etc. The leftmost column, which says number of coefficients, includes also the constant. So when you see coefficients equals to 2, it means that this is the best model with a single predictor and an intercept. And which single predictor would it be? If I only allowed you to use a single predictor, the best one would be neighborhood west, as you can see in the top row in this table. Then we see the top performing model with 2 predictors, which has coefficients equal to 3. And we see that the best pair is going to be whether you're in the west neighborhood and whether your house is a brick house or not. And similarly, you can compare other models that have a different number of predictors in them. The next step is to compare across these. So which one should I choose? A single predictor, the best pair, the best triplet? And we can compare these by looking not at R squared. Remember, R squared is not a very good metric for prediction. In fact, R squared would not even be appropriate for description because R squared depends on the number of predictors that you have. Adjusted R squared would be more appropriate. Let's focus on CP. CP, also called the Mallows CP metric, is a predictive metric. And what you're trying to do here is to find a CP value that is approximately equal to the number of coefficients. So looking at this table, which one of these models do you think the CP is favoring? Look carefully and you'll notice that the model that has either 6 or 7 coefficients is probably going to have better predictive accuracy. Now, no one said that these models have good predictive accuracy, but compared to other models, these are more likely to be better. The next step would be to try out these models. So in XOMiner, there's actually a link where you can click and it will automatically run that model. But the idea is don't stop here and choose a model. You actually have to go run it and evaluate it. Let me run a model that doesn't have the north neighborhood in it. Remember that the top 2 models looked like one that has all the predictors and the other one had all the predictors excluding the north neighborhood dummy. So to compare the two, let's actually run the model that has only 5 predictors or 6 coefficients. Here's the model, and the question is, how do we determine if this is a good model or not? Well, if we're going to stick to statistical significance, we might make mistakes. So although many of the predictors here are significant, bedrooms, for instance, has a p-value of 0.11, which might be considered high. However, this doesn't tell me anything about predictive accuracy. In order to determine that, you'd have to take out the bedrooms predictor and see how well you're predicting. Okay, so don't rely solely on p-values. Comparing the training and validation performance, we see that the average error is drastically larger in the validation set, which is indicative of something going wrong here. Maybe there is some outlier that's causing this problem. In terms of the RMSE, the numbers are more similar to each other. Let's compare the model with all predictors, that was 7 coefficients, to the model with 6 coefficients, the one that we just saw right now. We're trying to choose between the two in terms of using one for predicting new houses, house prices. So which one is better? Compare the average error on the validation data. Compare the RMS error on the validation data. Is there a drastic difference between them? Well, you're going to have to bring in the practical magnitude as well. Remember that RMS error and average error are in, their scale is exactly the scale of the data. So the average error here is telling you that the average mistake in pricing is about $120 versus $185. Are you happy with an average error of $185, or do you want an average error of $119? Well, you're always going to prefer a small model to a big one if the small one is performing adequately. Small models are more robust. They're easier to use. They're easier to run. They require less data collection and less data cleaning. And that's what we call parsimony. So if the smaller model performs according to requirements, or at least as well as you want it to perform, then always prefer that over a larger model. In this case, the model without the north neighborhood performs reasonably well. So to summarize, when we're talking about prediction, we don't care about interpretation that much. And in that sense, we can put in interaction terms and we can put in some crazy functions of predictors such as squares and square roots and not worry so much about, oh, we won't be able to interpret the coefficients. Second thing to remember is statistical significance. You can glance at it, but that's really not the way to choose your predictors. We didn't perform residual analysis here. It can be useful for determining transformations that can help with prediction accuracy, but it is not pivotal in terms of creating decisions that are correct or incorrect, as they are in descriptive modeling. And what we care most about is measuring predictive accuracy on a holdout set and choosing parsimonious small models that work reasonably well over larger models. Now, it might seem like we're just fishing around and trying out all kinds of things and running stepwise procedures to choose the best subsets. Well, hold on. Domain knowledge is pivotal to even using linear regression for prediction. You have to talk to the domain person to determine which inputs even make sense. It doesn't mean that you shouldn't try inputs that they didn't think about and you might have in your data, but you want to keep asking the domain expert, what are these measurements? How do they relate to pricing? Will they be available at the time of prediction? We're going to need this domain expert throughout the process in order to come up with a model that is reasonable from a business point of view. The last stage, as I mentioned before, is deployment. And when you're happy with your final model and you got a little glimpse of the process until model performance evaluation and choosing a final model, then we can actually go ahead and deploy this model to a whole new set of houses in mid-city. And different software packages will have the ability or not of scoring new data. Scoring means predicting new data. To summarize, linear regression models are useful for two very different goals. They're useful for describing a relationship in the population, and they're useful for predicting values of new records in the future. And what you see here are two pictures where the theme here is the newspaper. And what we're trying to say here is that the same tool, a statistical linear regression or a newspaper, can be used for very different purposes, but you would use it in a different way. And you would require different qualities. For example, if you're trying to read the news in the morning, it's very important that this is a recent newspaper, that the news are fresh. that the data has the newspaper has a format that you can hold and read with your coffee. In contrast, if you're using the newspaper to wrap fish, you don't really care about freshness of the news. What you really want is paper that can absorb moisture. So same tool, but you'll get very different models for each purpose. So keep the purpose up front in mind. Description versus explanation is going to be not only in the context of linear regression. This is true for many other tools. And you always have to keep in mind, how do I translate the business objective into either a descriptive or a predictive modeling objective? Because the paths are going to be completely different. Remember that in explanatory and descriptive modeling, we're going to be using statistical tests. We're going to be looking at the meaning and interpretability of the regression coefficients. And we're going to use residual plots to check for assumptions which are crucial for making any type of statement based on the model. In contrast, if you're going the predictive path, you're going to check very carefully that your predictors are available at the time of prediction. You're going to evaluate predictive accuracy using the data partitioning idea. And you're able to use automated variable selection to choose subsets of variables of predictors that give you high predictive accuracy. To close, I just want to mention a very interesting article that just came out in Harvard Business Review. And the article is called Big Data, the Management Revolution. A link is included on the website. There's a box inside this article that talks about expertise from surprising sources. And let me read a certain part. So two researchers had no special knowledge of the housing market, and they were trying to predict house prices, very similar to our example, in metropolitan areas across the United States. So I'm reading from the third column at the bottom. They had no special knowledge of the housing market when they began their study, but they reasoned that virtually real-time search data would enable good near-term forecasts about the housing market. And they were right. In fact, their prediction proved more accurate than the official one from the National Association of Realtors, which had developed a far more complex model, but relied on relatively slow changing historical data. This is hardly the only case in which simple models and big data trump more elaborate analytics approaches. Researchers at the Johns Hopkins School of Medicine, for example, found that they could use data from Google flu trends to predict surges in flu-related emergency room visits a week before a warning came from the Centers for Disease Control and Prevention. Similarly, Twitter updates were as accurate as official reports at tracking the spread of cholera in Haiti after the January 2010 earthquake. There were also 2 weeks earlier. I can tell you from my personal research in biosurveillance and early disease detection that this is true. Sometimes you have to move away from descriptive models and explanatory models into the predictive realm in order to discover very useful algorithms that can predict much better than the current descriptive models. I hope you've seen and evaluated the difference between using regression for prediction and for description, and that you'll notice how powerful linear regression can be with all the different tweaks that we can build into it for fitting data.